Okay, students, let's do some more problems. Let's work on some more problems here. Okay. All right, we're on chapter 23, and we want to look at page, let's see, we got chapter 23. We're on page 832, okay? So let's look at number 10, all right? It says, what is the equivalent resistance of each group of resistors shown in figure 23.10? Okay, 23.10. Of course, you have a couple of different diagrams here, resistor diagrams. Okay, and the first one, A, diagram A, and we got point A, and we come in here and we look like this right here. That's point B. And this is a 2 ohm, and this is a 3 ohm, and this is a 6 ohm, okay? And then we have diagram B, and it's really not much different. I don't know why I put those letters in there. We're not doing capacitance or anything like that. Okay, so we got one that comes in here and then comes down and does this. It's really not any difference. It's the same type. And this is a 3 ohm, and this is a 3 ohm, and this is a 3 ohm. This is really easy, okay? This is really, really easy, all right? All right, notice our configuration. Both of them are in series. And you say, well, how do you know that? There's only one pathway for current to flow. If I take any of these resistors out, we break the pathway for current to flow, and the circuit will not work. So it's a singular pathway for current to flow. Same thing down here on diagram B, okay? So if you remember, the REQ for series is equal to R1 plus R2 plus dot, 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 how many ever you have, okay? So looking at this one, we got the R equivalent, and I believe that is what it's wanting us to do, the R equivalent resistance. So we got the 2 ohm plus the 3 ohm plus the 6 ohm equals to 11 ohms, okay? So we'd have 11 ohms on that diagram, and then on this diagram, REQ is equal to 3 ohms plus 3 ohms plus 3 ohms, which actually we could say, let's see, 3 plus 3 plus 3 is 9, or we could say 3 times 9 since they're all the same. And so we get what? 9 ohms, don't we? Okay? Well, that one's so easy, I'm almost ashamed to give it to you, okay? So that would be the answers for 10A and 10B. Very easy problem, okay? Very, very easy. All right, now let's skip on over to the next page. Let's look at page 833, and let's look at number 28, okay? Number 28. 28's a little bit more complicated, okay? So I try to keep you honest in here. Okay, let me turn to my notes. Number 28. Okay. Now notice, let's first draw the diagram. It says find the current through and the potential difference across each resistor in figure 23.28. Okay, so let's draw it first. You always draw your diagram. And we got 10 volts DC. And so we come up here and we've got a resistor here, and then we come down, we have one here, and let's just go on back around. And then we come over here and we got one right here. That's connected, by the way. And then we come over here, we've got one like this. Okay. Now let's label each one. We got 5 ohms. This one's 5 ohms. This one's 5 ohms. And this one's 5 ohms. Well, they're messing with us, aren't they? 5 ohms, okay? All right, well, the first thing you have to do in a complex circuit diagram like this one, and this one's not complex at all, but the reason I say complex is because you actually have the combination of series and parallel types of circuits in this particular diagram, okay? You say, well, Mr. Shields, how do we know where to start? Well, you always go all the way out as far away from your voltage source as possible. Or I would say that's one way of putting it. But you also look for your parallels and your series. Notice this one's in series, but notice these three are in parallel. Notice how they are all parallel to each other. So these three are in parallel. Well, we know that the REQ, that 1 over REQ is for a parallel, is equal to 1 over R1 plus 1 over R2 plus dot, 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 how many ever you have. So notice we've got three in parallel here. They're all in parallel. How do you know they're in parallel? You have alternate pathways for current to flow. You see that right there? Alternate pathways for current to flow. So these are all in parallel. These three are. So we got 1 over REQ, which is equal to 1 over 5 plus 1 over 5 plus 1 over 5. Well, gee, the common denominator is what? 5. And so we wind up with what? Well, 5 going to 5 one time. 1 times 1 is 1. So we end up with what? 3/5. And, of course, we got to get to REQ, not 1 over REQ. So we take the reciprocal of that, and we get 5/3. But now we're not going to leave it that way. We're not going to leave it 5/3, okay? We're not going to leave it 5/3. We're going to do what? We're going to divide 5 by 3, of course. Okay, divide by 3, and you get 1.67. So we're going to round that up to 1.67 ohms, okay? Now let's redraw the circuit. Let's condense it down. And so we've got 10 volts right here. And so we come up and we've got 5 ohms now. And now we've got this one that's a combination of those three in parallel. That is 1.67. Dang it. Don't tell me I just erased it. And I did. Oh, that irritates me. Okay, we're number 28. Okay, we already had that part drawn. You can back the video up. I'm going to just draw the latter part of this circuit. You can back the video up. You're not going to die. Okay. I'm not going to redraw the other circuit. This one was 5 ohms. This is 1.67 ohms, okay? All right, now notice. Now remember, that's the combination of those three 5 ohm resistors in parallel. Notice this is in series, so we know the REQ for series, we just add them up, don't we? Plus 1.67 ohms, and so what do we get? We get 6.67 ohms is what our equivalent resistance is. Now you say, well, now why are we doing that? Well, because we have to find our equivalent resistance before we can go any further. Because notice it says find the current through and the potential difference across each resistor. Well, I'm actually going to have to go ahead and redraw the circuit to do this properly. So I'm going to go ahead and redraw it. Make everybody happy. I really need to anyway. Okay. So we come in here. And these are 5. And this one 5. I got to work on my Greek letter omega. Okay. Colonel Stamper would be aggravated at me. Okay. All right. Now we got to find the current through and the potential difference across each one. Okay. Well, oh, and by the way, y'all were saying this. You got to condense that down into one resistor to do equivalent resistance. You're exactly right. So you're going to come in here and it's going to be 10 volts. And we're just going to come over here and do it like that. And that's going to be 6.67 ohms, okay? 6.67 ohms. All right, now, you could actually carry it out one more decimal place and say 6.667. You could, but that's good enough, okay? That's close enough, all right? Now, we've got to find the current. So what do we got to do? We've got to find the total current, okay? Let's find the total current. Well, we know Ohm's law says that the voltage is equal to current times the resistance, so the current then is equal to the voltage divided by the resistance. So let's find the I total for the circuit. And so we've got what? 10 volts divided by 6.67 ohms. And what do we get? Well, we get 10 divided by 6.67. And we get 1.499. Let's just say 1.5 amps. So we're going to say 1.5 amps, okay? Now that's the total amperage. That's all the amperage that circuit has. Now you say, well, why is that important? Well, because here's where we have to use our rules for series and parallel circuits. All right, so we got 1.5 amps. Now notice that these two are in series, the 1.67, which was a combination of those three, and that are in parallel, and then this one. Now what do we remember about resistors that are in series? We know that the current is the same. So there is 1.5 amps here, and there is 1.5 amps right there on that one, okay? So this one has 1.5 and this one has 1.5 amps, all right? Now, let's find the voltage drop, and let's just go ahead and do it and get this one out of the way. Let's find the voltage drop right here, okay? Well, what do we remember about, and you say, well, now again, how'd you know that? Well, because look, these are in series. Look, these two are the combination of our final equivalent resistor. They're in series, so they have to have the same amperage, okay? All right, now let's find the voltage drop. Well, again, we use Ohm's law, so the voltage on the 10 is equal to what? The voltage on the 5 is equal to what? Well, we got 5 ohms times the resistance, current times resistance, resistance times current, doesn't matter, 1.5 amps, and what do we get? We get the voltage on the 5 is what? Well, 5 times 1.5 is 7.5 volts, okay? So that is 7.5 volts, all right? Now, this can be really easy. You say, well, now, how do I know what the voltage and the current is on these other 5, these 3 that are in parallel that are 5? Okay, since these are all the same resistance, we can do this. We can say, look, well, we started out with 10 volts. We used 7.5 on that one. So 10 minus 7.5 is what? 2.5 volts. So now look, 2.5 volts is going to drop here, here, and here. Okay, so we're going to drop 2.5 volts in all three of those 5 ohm parallel resistors. Okay. Now, what about the amperage? Okay, well, we know that there's 1.5 amps here on the combination. Since they are all the same resistance, we can split that 1.5 amps divide 1.5 by 3, and what do we get? Well, each one of these will have 0.5 amps on each one. Okay, and you say, well, now, how did you know to do that? Because they're all the same resistance, therefore, they have to have the same amperage, all right? And again, each one's going to have 2.5 volts, 2.5 volts, and 2.5 volts. And you say, well, Mr. Shields, I wish you'd show me how to do that. Calculate it. Okay, well, let's calculate it. All right, which one we want to do first? It doesn't really matter, I guess. We know that there's 1.5 amps. Okay, well, 1.5 amps times 1.67 is what? 1.5 times 1.67, and you get what? 2.5. Did you see how I did that? Let me show you again. So we got, what's the voltage on all of these? Well, we know that since they're going to have the same voltage across each one because they're parallel, we just say 1.67, all right, times 1.5 amps, okay? That's the voltage on all the 5s, and that's going to be 2.5 volts. All right, now what about the amperage? Well, how do we find the amperage? Well, we know there's 2.5 amps across each one, right? Well, yeah. Okay, well, then the current on each one will be what? Well, the voltage, which is 2.5, divided by 5 ohms, and what do you get? Well, you get 0.5 amps, okay? So see, it does work out, and each one of those will have 0.5 amps. Because when you add them all up, what do you get? You get 1.5 amps, okay? All right, I hope that helped on that one. All right, let's look at another one. Let's look at number 40. I think we have a capacitor, yeah. Let's look at number 40. I think number 40 is on the same page. Yeah, page 833. Yeah, so page 833. All right, so number 40. Let me get to my notes. All right, there we go. All right, so number 40 says, what is equivalent capacitance of the 3 capacitors in figure 23.4? All right, so let's draw it. We got 23.4. What is the equivalent capacitance? All right, so we got our circuit looks like this right here. We got a capacitor here, and then one like this, and then it comes around. I wished it wouldn't do that. And then it comes over here, and we got a capacitor like that. Now, this one right here is 20 microfarads. This one right here is 30 microfarads. This one right here is 25 microfarads, okay? And don't forget, micro is 10 to the negative sixth, okay? So what is equivalent capacitance, all right? Okay. Well, folks, we got to reduce it down to one capacitor, right? But now notice we've got two in series right here. These are in series, but then these two are parallel to this one, which is in series. You say, again, how do you know? Alternate pathway for current to flow, all right? Notice that current can go this way and current can go that way. So this branch and this branch is parallel to each other. So what is the equivalent capacitance? How do we do the equivalent capacitance for resistors in parallel? Do you remember, okay? All right. Well, for capacitors that are in series, we got to do these two first, okay? Got to do these two first because they're in series with each other. Remember, it's the reciprocal. So 1 over CEQ for series is equal to 1 over C1 plus 1 over C2 plus ... how many ever you have. Well, we've got two, so we've got 1 over CEQ is equal to what? 1 over 20. Now, I'm going to leave the scientific notation off because it's going to stay 10 to the sixth, okay? I'm just going to do it this way, 1 over 20 plus 1 over 30. All right, and we have to get a common denominator, and the common denominator would be what? 60? Would that be correct? I think it would be. Common denominator would be 60, so that would be what? We got a common denominator of 60, and so that's going to be what? Well, 20 will go into 60 three times, so 3 times 1 is 3, and 30 twice, so it'll be 5/60ths. Yeah, 5/60ths. Now, notice it's 1 over CEQ, but we got to make it CEQ, so we have to do what? As Colonel used to say, we got to flip it. So we flip it around, and it becomes what? 65ths, or 12 microfarads. All right, now let's redraw our circuit. So we come in here, and now we've got what? One capacitor here, and then we've got another capacitor right here, don't we? All right, now this one we just found to be 12. We've got to redraw our diagram. You always have to condense it down to one. Whether it's resistor or capacitors, you've got to reduce it all the way down to one, okay? Now, this one was 25, wasn't it? Microfarads. All right, now notice these two are parallel. Well, we know that the CEQ, EQ for parallel is C1 plus C2 plus ... okay? So the CEQ, for those in parallel, we got 12 microfarads plus 25 microfarads. I don't know what's going on with my pen. It's lagging behind. We got what now? 37 microfarads. Everybody agree? 37 microfarads. Now let's draw our final circuit. And it's going to look like this right here. You're going to have one capacitor. And that's 37 micro. That's 10 to the negative sixth farads. Okay? So that is the equivalent capacitance for that circuit. It's real easy, isn't it? Okay? You just got to be methodical. You got to follow your steps. Okay? All right, I hope this is helping. All right, let's do one more problem. I think we're going to do number 44. I believe that's right. Okay, yeah. All right, so number 44 says, what is the time constant for the discharge of the capacitor in figure 23.44? Okay, so we want to know the time constant for 23.44. All right, so let's draw the circuit. So we've got, and this is number 44, okay, and this is on page 834. So let's draw our circuit. We got a 10 microfarad right here, capacitor, and then we come up here and we've got a switch, and then we come down and we got a resistor here, and then a resistor here, and then we come back around, boom, like that right there. And we've got a 1 kilo ohm, we got a 1 kilo ohm and a 1 kilo ohm resistor, okay? And those are in series, okay? Now it says, what is the time constant for the discharge of the capacitor in figure 23.44? All right, well now we know that the time constant is pretty easy to find, isn't it? Basically the time constant tau is equal to the resistance times the what? The capacitance, and that's the equivalent capacitance or capacitance. In this case, there's only one capacitor. Okay, there's only one. All right, and that was that a 1 I'm sorry, y'all. My glasses are messing with me. That is a 1 microfarad. I'm sorry. My glasses are messing with me. That's a 1 microfarad, not a 10. I'm sorry about that. Okay, now, so it's real easy calculation. So we got tau is equal to the resistance. Now look, these two are in series, so just add them up. You're allowed to do that because they're in series. That's what we do for resistors in series anyway. 2 kilo ohms times what? The equivalent capacitance is 1 microfarad, which is 10 to the negative 6th. And so what do we get? Well, we got 1 to the negative 6th times 2 to the 3rd, and we get 2 milliseconds. 2 times 10 to the negative 3rd seconds, or 2 milliseconds, okay? Be sure you know how to use those prefixes, all right? Okay, I hope this helps. Well,